It's late. The kind of late when the refrigerator hum sounds like philosophy. You and I are awake with a glass of water and a question universe-sized. Why do black holes, the most silent things we know, talk back in riddles? The more we chase their truth, the more they slip into paradox. As if the cosmos hired a stand-up comic to roast our best theories. We call them black holes, but that name is just the cover of the book. Inside is a stack of contradictions tall enough to prop open the door to new physics. So tonight we go in softly, not with the all-caps thunder of equations, but with a whisper that threads you from kitchen tile to event horizon. Our itinerary is simple to say and hard to survive. 5 headaches that have fueled 50 years of arguments, bets, breakthroughs, and bruised egos. First, the information paradox. Quantum law says information cannot vanish. The black hole nods and swallows your notes anyway. Second, the singularity. General relativity insists there's an infinity hiding at the center, which is usually theory's way of screaming, "I'm out of my depth." Third, the shadow. If no light can escape, why did we see a black hole silhouette in glowing orange? Fourth, time and causality. At the brink clocks crawl, scenes disagree, and cause and effect starts to sound like jazz. Fifth, the existential one. What if nature never lets the fully legal textbook black hole actually form? What if we've been staring at convincing fakes? Before we unpack each, let's steady the camera. A black hole is not a thing in the normal sense. It's a place in space-time where the geometry makes a one-way turnstile. The boundary of that no-return region is the event horizon. Cross it going inward, and even light, our fastest courier, can't make it back to send a postcard. That's the operational definition, the practical mythbuster. We're not talking about a cosmic vacuum cleaner that hoovers the room. We're talking about a patch of space-time where all future paths point deeper in. From far away, gravity just looks like gravity. Near the horizon, it becomes a policy. But maps can lie by omission. In the 1970s, a quiet bomb dropped. The merger of black holes with thermodynamics. Jacob Bekenstein
宇
asked
宙に
whether a
は
black hole
およ
could
そ
have
2兆の
entropy,
銀河が存
a
在す
measure
る
of
こ
the
とについ
information
て
it hides.
皆さんは考えたこ
Then
とはあり
Stephen
ますか？
Hawking, with the patience
私
of a
たちの
monk
天
and
の
the
川
steel
銀
of a
河は
street
その
fighter,
中の一
found
つ
that
に過
black
ぎません。
holes aren't perfectly
そう、
black.
この銀河
They
は
radiate,
私たちの
not
宇宙の
sunlight,
家。
not
しか
even
し、純
starlight.
粋に理論上は
A
同
faint
じ確率で別
thermal
の銀河に
whisper
住んで
from
い
the
た可能性
quantum
もあるので
froth
す。
of space-time
皆さんこん
itself.
にちは。仮にそうだったとしたら、
Hawking radiation means black
地球は
holes
どんな
can
影響を
evaporate.
受けたのでしょうか。
We'll sit with that
な
shock
ぜ
properly in a
活動
later
銀河核
chapter,
を持つ銀
but
河
feel
は
the stage
知的
creep
生命
under
体
your
を探
feet
すのに
already.
適さないのでしょう
If the
か。
hole slowly
皆さん、
leaks out
こち
heat
らは
with
トッ
no
プランキング
memory,
です。
where does the
今回はその
information
すべて
go?
と他に
Did
も
the
たく
universe
さんの
just
話題をお
commit a
届けしま
felony
す。
against quantum
それでは
mechanics?
始めましょう。
That's our first paradox knocking, not with a battering ram, but with the chill of a locked door. And yet, decades after the arguments, we have a counter-whisper too, holography. The idea, audacious, almost rude, that the true ledger of a volume of space can live on its boundary. Think of it as cosmic bookkeeping. The inside story written on the surface, the way a city's history hides in the soot on its walls. That possibility, born in the theoretical forge that married gravity to quantum field theory, doesn't solve all puzzles, but it gives us a handle, a way to say, perhaps nothing was lost. Perhaps we were reading the wrong page. If black holes are the testing ground, they also became stage and spectacle. In April 2019, a global web of radio dishes stitched Earth into a makeshift planet-sized lens. And humanity glimpsed the unseeable, a ring of fire with a hole of night, M87's shadow. Not a portrait of the object itself, but its negative space, imprinted on incandescent plasma. 3 years later, our own galactic centre, Esker Ayan, took a turn, and the donut returned like a motif in a symphony. How did we see what cannot be seen? Is not a riddle. It's a lesson in gravitational lensing, in light bent into circles, in the way space-time sculpts images as surely as a lens crafts a photograph. We'll go there, carefully, because every claim deserves both the drumroll and the cross-examination. Time near a black hole is not your polite, linear calendar. It's a neighbourhood with strange zoning laws. Stand far away and watch a falling clock. It slows, reds, and seems to freeze at the horizon, an optical philosophy experiment. Ride with that clock and the fall is brisk, finite, alarmingly ordinary until it isn't. This mismatch doesn't mean physics contradicts itself. It means perspective matters. But admit it, the horizon feels like a magic trick you can't repeat at home, the kind that keeps philosophers and physicists awake for different reasons. And the centre. The centre is where general relativity shrugs. The equations, otherwise stately, elegant, predict a singularity, a point where density and curvature go to infinity, like telling you the speed limit is yes. Usually when infinity shows up in physics, it's the universe tapping the chalkboard. Your model was gorgeous, but incomplete. Maybe spacetime, zoomed in far enough, is grainy. Maybe strings replace points. Maybe the centre is not a point to begin with. Different camps, same confession. Classical gravity is missing quantum teeth. The fifth paradox is less a claim than a dare. What if nature stops collapse just shy of a true horizon? We have models, Graver stars, boson stars, other cleverly named what-ifs, each trying to mimic a black hole's outside look without signing the inside's legal documents. Most evidence we've gathered, from the orbits of stars whipping around an invisible anchor to the base note ring of gravitational waves after colossal mergers, points to real, honest to Einstein black holes. Still, the minority report is scientifically healthy. If there's a surface where there should be only horizon, then some light should splash back. Some ring-down notes should go sharp. So far, black holes sing on key, but we keep listening. Here's our pact for the journey. I'll keep the numbers in my back pocket and hand you metaphors first. You keep your skepticism sharp, but not sour. We'll revisit Hawking the gambler, Susskind the dualist, Beaconstein the quiet architect. We'll trace how the no-hair slogan, black holes characterized only by mass, spin and charge, grew asterisks in the age of quantum information. We'll walk the event horizon not as a cliff, but as a legal boundary, rights waived upon entry, appeals denied, and at every turn we'll test which paradox is a mirage of language, which is a signpost to new physics. For now, breathe with the dark. The refrigerator hum continues. The water glass sweats a small galaxy on the counter. Somewhere 55 million light-years away, a ring of radio-bright plasma orbits a shadow, and the shadow isn't an object, it's the absence defined by geometry. Somewhere else, in equations that don't sleep, islands float in entropy seas, promising that information, like good gossip, always finds a way out, encoded, delayed, but not dead. In the next section, we'll let the information paradox take the mic properly and see why a seemingly technical dispute about unitarity felt like sacrilege, and why the resolution may be less about loopholes and more about changing where we think the story is written. Midnight is the right time to ask impolite questions. Let's start with the rudest. If nothing escapes, how does truth survive? So let's unseal the first paradox like a letter stamped by the cosmos itself. The information paradox. At its core, it's deceptively simple. Physics, as written in the small print of quantum mechanics, tells us that information can never be truly destroyed. Burn a book and the smoke, the ash, the rising heat. If you were infinitely clever, you could, in theory, reconstruct every word from the dance of the particles. Information transforms, but it does not vanish. This is called unitarity, and it's a cornerstone of the quantum stage. Now put that book near a black hole, toss it in. The horizon swallows it without a burp, and here comes the scandal. According to Einstein's gravity, nothing escapes. Not the pages, not the ink, not even the metaphor. The black hole doesn't keep a diary of what it eats. To an outsider, it just looks gone. Imagine shredding an ancient manuscript, and instead of confetti, the shredder emits a hiss of static with no way to rewind. That is what troubled physicists for decades. The paradox sharpened in the 1970s when Jacob Bekenstein suggested black holes must carry entropy, a measure of hidden detail. Entropy in fact proportional to the area of the horizon, not its volume. That's like saying the secrets of a library are written not in the shelves but on the doors. Stephen Hawking at first resisted, then performed his legendary calculation. Quantum fluctuations at the horizon make pairs of particles, one falling in, one escaping. The escaping ones form Hawking radiation. The punchline: the radiation is thermal, featureless, like steam rising from a boiling kettle. It carries heat but not recipes. And here's the kicker: as the black hole radiates, it loses mass. Slowly, achingly slowly, it shrinks. Left long enough, longer than the current age of the universe for most, the black hole evaporates entirely. Nothing left. And if that's true, what happens to the information about the book, the astronaut, the unlucky pizza delivery guy who fell in? If the last puff of radiation carries no imprint of them, then physics just broke its own promise. This is the information paradox, and it's why Hawking set off a storm. He argued, information is truly lost. Others recoiled. Leonard Susskind, Gerard Tufte, and many others mounted the counteroffensive. No, quantum mechanics is too sacred to sacrifice. What followed was not a polite seminar, but a scientific brawl that earned its nickname, the Black Hole War. For 3 decades, conferences buzzed with this duel. Hawking, stubborn and brilliant, clung to his claim. Susskind and allies countered with holography, insisting the horizon must somehow encode everything that falls in. At stake wasn't just black holes, it was whether our deepest physical laws could be trusted. If information could vanish, so could predictability. The universe itself would be a badly run casino, cheating its players. And because scientists are human, the fight carried drama. Hawking and Caltech's John Preskill made a bet. If information survived, Hawking would concede with a token. Years later, when the tide turned, Hawking handed Preskill an encyclopedia of baseball, from which information could be retrieved at will. A joke, yes, but also an admission that perhaps the universe is fairer than his equations first implied. Still, even after Hawking's concession, the paradox lingers like an aftertaste. How exactly does the information leak out? Not in smooth, obvious streams, but, if the emerging consensus is right, in subtle quantum correlations laced into Hawking radiation. Think of it as static with a hidden watermark. Almost impossible to notice at first, but there, if your detector were impossibly sensitive. This realization gave rise to the holographic principle, which we'll meet in detail later. The revolutionary suggestion that a black hole's surface area records everything. Not a shred of history lost, just encrypted beyond our current reach. So why does this matter to you sitting in the dark with me? Because it strikes at the foundation of how reality works. Either black holes delete history, sacrilege to quantum mechanics, or they obey the laws but in a way that forces us to rethink what space and inside even mean. It's less about books and astronauts, and more about whether the universe is consistent, or whether at its most extreme, it cheats. And we're not done. If information does escape, how? Some theories say it trickles out encoded in the Hawking radiation. Others imagine the horizon itself acting like a cosmic hologram. Yet others, more radical, suggest a fiery wall waiting at the brink. In the next chapter, we'll peer closer at that Hawking radiation itself, what it is, how it works, and why the smallest glow from the darkest objects spark the loudest quarrel in modern physics. Because sometimes the faintest whisper is the one that rewrites the script. Let's stand closer to the bonfire Stephen Hawking lit in the 1970s, the one that set the physics community arguing for decades. The bonfire wasn't flames, of course, but radiation, the very thing black holes were supposed to reject. Here's how it works, told without the chalk dust. Space isn't empty. Even in the deepest dark, the vacuum is buzzing with virtual particle pairs popping into existence. One positive, one negative, before annihilating each other again, like a magician's coin trick. Near the razor edge of a black hole, the event horizon, this coin trick stumbles. One particle falls in, the other escapes. The escapee shows up as Hawking radiation. And this is the shocker. Black holes aren't eternal. They leak. Ever so slowly they radiate away energy, shrink, and eventually evaporate. It's like discovering that your indestructible safe has a tiny hole in the back where all the gold drips out, grain by grain, over billions of years. At first, physicists were amazed. Hawking had connected quantum mechanics, gravity, and thermodynamics in one audacious calculation. But amazement quickly soured into crisis, because the radiation is thermal, random. It tells you nothing about what fell in. Toss in Shakespeare, and the outgoing glow is indistinguishable from tossing in yesterday's laundry. The radiation is just heat. This deepened the information paradox. If the whole evaporates entirely, all the detail, the microstate, the quantum bookkeeping of what fell in, appears gone forever. Not just
宇宙に
hidden,
は
but
およそ2
erased.
兆の銀河が存在す
Imagine
ること
burning
に
a
つい
love
て
letter, and
皆さんは
instead
考
of
えた
smoke
ことはあ
carrying
り
the
ますか？
faintest trace of
私
words,
たちの
the
天の川
universe
銀河は
responds with
その中の
identical
一つに過ぎま
static
せ
no
ん。
matter what was
そう
written.
この銀河は私た
That
ち
would
の
be a
宇宙の
violation
家。
of unitarity,
しかし
one of
純粋
physics'
に理論
holiest
上は
commandments.
同じ確率で
Physicists
別の
don't
銀河に
like
住んでいた
commandments
可
being
能性もあるの
broken.
です。
Cue the
皆さん
uproar.
こんにちは。
Some tried to
仮
argue
に
that
そうだっ
maybe
た
the
としたら
information was
地
lost.
球はどんな
Perhaps
影響を受
quantum
けたのでしょう
mechanics
か。
itself wasn't as
なぜ
strict as we
活
thought.
動銀河核を持つ
Others
銀河は
refused to
知的
budge.
生命体を探すの
Surely
に
they
適さない
argued
の
the
でしょう
laws
か。
of nature aren't
皆さ
sloppy.
んこちらはトップランキングです。
Somehow,
今回はその
the
すべて
information
と
was being coded.
他にもたくさんの話題をお届けします。
Characteristically bold,
それで
double
は
down.
始めましょう。
He insisted the universe allowed this deletion. It was his hill to die on. But even he later backtracked, famously conceding after 3 decades of dueling with his colleagues. The concession wasn't just theoretical, it was theatrical. At a conference in Dublin in 2004, Hawking announced he had changed his mind. Information could, after all, escape. To mark the occasion, he handed over a baseball encyclopedia to John Preskill, from which information could be retrieved at will. Science with a side of humour. Yet the question remained, how does it escape? Hawking's mathematics never gave a clear mechanism. Instead, it left us with a mystery bigger than before. Some suggested the radiation is subtly correlated, tiny patterns hidden in what looks like random noise. Others leaned on the holographic principle, which whispers that everything inside might actually be stored on the horizon's surface. Think of it like a cosmic USB drive, etching data on the event horizon while pretending to be a bottomless pit. And still, new ideas keep arriving. In the past decade, physicists revived the discussion with the so-called island formula, a clever way of calculating entanglement entropy that hints the information isn't lost, but rerouted in ways we're only beginning to glimpse. It's the kind of result that makes graduate students stare at whiteboards until sunrise. For you and me, though, the takeaway is sharper. Hawking radiation turned black holes from eternal tombs into ticking clocks. Every black hole is temporary. Every black hole leaks secrets, though in whispers so faint we may never hear them directly. And every black hole forces us to ask whether reality itself is faithful to its own rules. Next, we'll step into the storm these debates unleashed, the 30-year Black Hole War. A battle fought not with swords, but with equations, egos, and occasionally petty humour. And if you think physicists are mild-mannered, you've never seen them argue about the fate of the universe's information. Picture a war room without smoke, without trenches, just chalkboards, overhead projectors, and egos large enough to bend light. This was the Black Hole War, a battle that raged not in deserts or oceans, but in the hushed halls of physics departments and the caffeinated chaos of conferences. The generals, Stephen Hawking on one side, Leonard Susskind and Gerard 't Hooft on the other. The weapon of choice, equations, thought experiments, and an occasional cutting joke. Hawking's position was blunt, almost punk rock. Information dies in black holes. Drop your wedding photos, your favourite vinyl, or the complete works of Shakespeare, and the universe shrugs. What comes out is thermal radiation, featureless, meaningless. To Hawking, that was it. Quantum mechanics, he said, might need to accept a dirty secret. Sometimes information just disappears. Susskind and others were horrified. To them, this was sacrilege. Quantum theory wasn't just one more law. It was the law, the one that had delivered lasers, transistors, and the weird certainty that probabilities rule the microscopic world. If information could vanish, quantum mechanics would crumble, and physics itself would wobble like a bad table. Thus began the debates, stretched over conferences like a long-running soap opera. Hawking, brilliant but stubborn, defending his claim with unmatched confidence. Susskind, scrappy and relentless, insisting that black holes must be consistent with quantum principles. Others joined the fray, Tufte sharpening the holographic principle, Kip Thorne observing from his own perspective, John Preskill waiting to cash in on a bet. And yes, there was a bet. In 1997, Hawking and Thorne wagered against Preskill. Information is lost. If Preskill won, Hawking would hand over an encyclopedia of his choosing. It became physics' most famous gentleman's gamble. When Hawking eventually conceded in 2004, he gave Preskill a baseball encyclopedia, because of course, it was both humorous and humiliating. From which, Hawking quipped, information can be retrieved at will. But don't mistake this as light banter. For 30 years, this question wasn't academic trivia. It was existential. If Hawking were right, then quantum theory, the very system we use to predict everything from chemical reactions to computer chips, would need rewriting. If Susskind were right, then Einstein's elegant black hole description was incomplete. Either way, someone's hero was going to take a hit. The debates became legendary. Physicists would stand at blackboards late into the night, sketching event horizons, arguing over whether information was smeared on the surface like peanut butter or hidden inside forever. Some students recalled the tension of those talks like watching gladiators, but with chalk dust instead of blood. And here's the beauty. This wasn't petty infighting. It was science in raw form. Arguments sharpened not by politics, but by the stakes of truth. The clash gave birth to whole new frameworks. Holography, add CFT correspondence, string theory, fuzzballs. Out of disagreement came creativity, as though paradox itself was a forge. Eventually the tide turned. Evidence for the holographic principle grew. Theoretical models showed ways the information could, in principle, escape encoded in subtle correlations. Hawking, after decades, relented. The war didn't end with one side obliterated, but with a handshake across the battlefield, a messy human resolution to a cosmic riddle. And yet, the scars remain. Because even today, the exact mechanism of how black holes save the books they eat isn't fully nailed down. Did Hawking's radiation always carry the data, like a coded whisper? Is the event horizon itself a ledger? Or is the whole inside vs outside story wrong, a trick of perspective? In the next part, we'll follow the thread that ended the war, the radical idea that space itself is a hologram. It sounds like science fiction, but it may be the universe's best-kept secret. That the true description of reality lives not in the volume, but on the surface. And so, in the ashes of that long war, out of the chalk dust and bruised egos, a strange idea began to shimmer. The holographic principle. Let me whisper it in the midnight way. What if the entire universe is a kind of cosmic DVD? The three-dimensional story we live inside is projected from a two-dimensional surface we can't step outside of. That sounds like sci-fi philosophy, but it emerged from the hard grind of theoretical physics. Gerard Hooft first sketched the thought, when matter falls into a black hole, the information about it isn't lost in some unreachable singularity, but encoded, like carvings, on the event horizon itself. Leonard Susskind took the torch and ran with it, coining and popularizing the holographic principle. The claim is audacious. The interior of a black hole is not a secret abyss, but a holographic illusion generated by surface data. If true, this means when you toss Shakespeare's plays into a black hole, the scripts aren't incinerated. They're smeared, holographically, across the horizon. No librarian is lost. Just the shelving system changes. This principle found its sharpest mathematical teeth in the add CFT correspondence. a duality discovered in the late 1990s by Juan Maldatina. In that framework, the physics inside a curved spacetime, anti-de Sitter space, is exactly equivalent to a quantum field theory living on its boundary. The inside and the surface are two languages telling the same story. One is gravity plus strings, the other is no gravity, just fields. But both describe the same reality. For black holes, this is a revelation. It suggests that all the data swallowed, the microstate fingerprints of what fell in, resides not hidden but accessible, etched onto the horizon like cosmic graffiti. What looked like loss is really relocation. Think about the shift in perspective. The paradox that drove Hawking and Susskind to intellectual war suddenly bends into something more elegant. Black holes may be holographic libraries, not shredders. They don't destroy books, they translate them into a language only the horizon can speak. And outside black holes, the principle may extend to the entire universe. If true, then what you and I call space, this living room of stars, might be the holographic projection of data stored on a distant boundary we'll never reach. We might all be characters written on the edge of the universe, unaware we're just the novel. But let's not get ahead of ourselves. Back to the black hole itself. The holographic principle didn't just resolve old debates, it reframed the battlefield. It showed that paradox is often not a true contradiction, but a sign we're asking the question in the wrong coordinates. Inside versus outside might be like north versus south on a globe. Real distinctions locally, but illusions globally. And yet, holography doesn't end the story. It hints, it winks, but it doesn't hand us the final page. Because if the horizon encodes the information, we still need to know how it's returned when the black hole evaporates. Is it dripping out, coded in Hawking radiation? Does it emerge only at the end like a final confession? Or is the very picture of evaporation flawed? In the next part, we'll follow the latest whispers, the island formula and the rebirth of the page curve, how new techniques suggest that information might reappear, not at the last puff, but gradually, leaking back as the black hole shrinks. It's like learning that the universe isn't just burning a letter, it's sending fragments of the message back in the smoke all along. So far, we've painted black holes as ultimate shredders that maybe, just maybe, keep a secret backup on their surface. But physics is greedy. It wants more than metaphors. It wants equations, predictions, timelines. That's where the island formula steps onto the stage, carrying with it a twist worthy of a midnight detective novel. Here's the riddle. How does the entropy, the messiness of information, actually change over time as a black hole evaporates? If Hawking's original calculation were right, entropy would just keep climbing, like an ever-mounting junk pile of random radiation, until the black hole vanishes and leaves behind a cosmic trash heap of meaningless static. But if information is preserved, then the curve should bend back down. Radiation entropy should rise for a while and then decline, reflecting that the outgoing particles do, in fact, encode the lost data. This theoretical sketch of entropy versus time is called the page curve, after physicist Don Page, who drew it long before the math was available. For decades, it was a prediction without proof, a doodle of hope pinned against Hawking's grim calculation. Then, around 2019-2020, something extraordinary happened. Teams of physicists used the tools of holography and quantum gravity to actually compute the page curve, not with hand-waving, but with serious math. Their secret ingredient? Islands. Now don't imagine palm trees and coconuts. These islands are regions of space-time
宇宙
inside
に
the
は
black hole
およそ
that
2兆の銀河が存在
counterintuitively
することにつ
must
い
be
て
included when
皆さんは
calculating
考
the
えたこ
entropy
とは
of
あ
the
ります
outside
か？
radiation.
私たち
It's
の
as
天の川
though,
銀河
in
は
tracking
その
smoke
中の
signals
一つに
drifting
過ぎ
away,
ません。
you suddenly
そう、
realize part
こ
of
の
the
銀河は
fireplace itself
私たちの
counts
宇
as
宙の家。
outside.
しかし、
By adding
純
these
粋に
islands
理
to the
論上
ledger,
は
the
同じ
math
確率
reveals
で
something
別の銀河に
stunning.
住んでいた可能
The
性もある
entropy
のです。
curve bends.
皆さんこんにち
It
は。
follows the page
仮にそうだった
prediction,
としたら、
which
地
means,
球はどんな
at
影
least
響を
in
受けたのでしょ
principle,
うか。
information
なぜ
does make
活
its
動
way
銀河
back
核を持
out.
つ銀河は
Think
知的
about the
生命体を
audacity
探
of
すの
this
に
move.
適さないのでしょ
We're
う
used
か。
to separating
皆
inside
さん、
from
こ
outside
ちらは
with
トップラン
religious
キングです。
devotion,
今回はその
event
すべて
horizon,
と他にもたくさんの話題をお届けしま
but
す。
the island formula
それでは
below is that
始めま
line.
しょう。
letting the interior leak into the exterior's bookkeeping. It's not so much breaking the rules as discovering they were written in finer print. Of course, this breakthrough doesn't mean we can go scoop our lost astronaut's diary from the Hawking radiation tomorrow. The correlations are vanishingly subtle, tangled in quantum entanglement patterns so delicate that no detector we can build could decode them. But the principle matters. The math now supports what quantum mechanics demanded all along: unitarity. Information survives. The universe, messy as it is, doesn't burn its receipts. And here's the kicker. This wasn't just a patch job. It was a sign of a deeper harmony between gravity and quantum theory. Physicists like to say the black hole is the hydrogen atom of quantum gravity, the simplest, most revealing system for testing unification. The island formula was like finally cracking a code word written in the margins of spacetime, whispering that the two great frameworks can, at least occasionally, dance in sync. But, because there's always a but, the story doesn't end here. Islands solve one riddle, but they raise another. If part of the black hole's interior is secretly outside, what does inside even mean anymore? Is the horizon a real boundary, or just a mirage of perspective? And what happens to the poor traveller who actually crosses it? Do they fall into smooth space-time, as Einstein promised, or slam into something far nastier, like the infamous firewall? In the next chapter, we'll peer into that terrifying possibility: a wall of flame at the edge of every black hole, ready to barbecue any infalling astronaut. A solution so drastic, it makes you wonder whether the universe has a sadistic sense of humour. Now comes the part of the story where physics flirts with horror fiction. You've probably heard the comforting line, if you fell into a black hole, you wouldn't notice crossing the event horizon. Einstein's relativity paints it as a smooth ride. You'd pass the invisible boundary without fireworks, only realizing something was wrong when tidal forces finally stretched you like pasta. That calm promise has lulled generations of physics students. Enter the firewall paradox. In 2012, a group of physicists, Ahmed Almeri, Donald Meroff, Joe Polchinski, and James Sully, published a bombshell. To keep information safe, they argued, the horizon might not be smooth at all. Instead, it could be a wall of high-energy radiation, a firewall. Anything crossing it would be instantly incinerated. Goodbye smooth fall, hello cosmic crematorium. Why would anyone propose something so brutal? Because of a tug of war between three principles that normally coexist happily. Unitarity. Information can't be lost. Relativity. The horizon should feel smooth to the infaller. Quantum entanglement. Hawking radiation must be entangled in just the right way to carry information out. The problem? You can't keep all three. The math shows that if you insist on saving information, something's got to give, and relativity's smooth horizon is the weakest link. Result: a firewall. It's an unsettling thought. Picture an astronaut approaching the horizon, expecting the silence of infinite gravity, only to be obliterated in a blaze of quantum fire. No journey to the singularity, no graceful end. Just a fiery curtain that no one can cross, but not everyone buys it. To many physicists, the firewall hypothesis is like a horror movie twist that ruins the franchise. General relativity has been so successful that tossing its smooth horizons into the flames feels like sacrilege. Others point out that the paradox may dissolve once we fully understand quantum gravity, that firewalls might be a mirage born from mixing half-finished theories. Still, the idea sparked a storm. Conferences became battlefields again. Was the firewall a real feature of nature or a mathematical dead end? Some argued it was just a placeholder for a deeper solution, perhaps holography again. Others leaned into it, saying, maybe reality is crueler than Einstein imagined. And here's the eerie part. We can't test it. No probe we send, no telescope we point, can peek inside a horizon to see what happens. The firewall is a ghost hypothesis, one we may never confirm or kill. So where does that leave us? Somewhere between comfort and nightmare. Black holes might be smooth portals into warped space-time, or they might be fiery buzzsaws at the edge of existence. And until quantum gravity hands us a complete manual, both options sit uneasily on the shelf. But black holes aren't done toying with us. Because if the firewall paradox unsettled us about the horizon, the next paradox takes us straight to the core. The singularity itself, that little mathematical monster where space, time and reason go to die. Step closer, past the event horizon, past the firewall debate, into the place no one has ever seen, but everyone has an opinion about, the singularity. General relativity, Einstein's proudest child, doesn't stutter when it tells you what's at the heart of a black hole. It says, compress matter hard enough and gravity wins. It crushes stars not into diamonds, not into neutrons, but into a point. Zero volume, infinite density, a singularity, infinity. Physics usually treats infinity the way you treat a fire alarm. It means something has gone terribly wrong. If your math spits out a number that never ends, it's not a discovery, it's a confession. It's the universe saying, your model doesn't apply here. Yet the singularity sits there, lurking in the equations like an embarrassing family secret. At the black hole's centre, the curvature of space-time becomes infinite. Time itself ends. And the laws we know stop working. Relativity, so good at predicting planetary orbits, GPS signals, and even gravitational waves, just throws up its hands. Think about the irony. Black holes are the ultimate victory of general relativity, the shining evidence that Einstein's math describes reality. And yet, at their core, those same equations eat themselves alive. It's like writing the perfect symphony, only for the final note to shatter the instrument. Some physicists take this literally. Maybe singularities exist, places where the laws collapse and reality simply has no script. Others recoil. They argue infinities aren't real. They're the universe's way of saying you're a get a better theory. And that better theory is the holy grail, quantum gravity. If gravity is geometry and quantum mechanics is probability, then quantum gravity must be the awkward marriage of the two. And many suspect that once it's written, singularities will vanish from the guest list. The infinite will be replaced with something finite but exotic. Perhaps a bounce, a core of quantum foam, or something stranger than we have words for. Already rival camps are sharpening their answers. Loop quantum gravity suggests space itself is grainy, like pixels on a screen. Try to compress it beyond a certain limit and you can't. The granularity pushes back. No infinity, just a rebound. String theory, on the other hand, whispers of fuzzballs, tangled knots of vibrating strings that smear out the singularity into something more like a dense star of quantum spaghetti. Different answers, same ambition, banish infinity. But until quantum gravity arrives, the singularity remains the dragon on the map. The place labelled here, but monsters. And for all our metaphors, the real bite is this. The singularity is where our ability to predict the future dies. Normally, physics is about forecasting. Give me the present, and I'll tell you what comes next. But if reality truly ends in a singularity, then the chain of cause and effect breaks. The story cuts off mid-sentence. That's why the singularity isn't just a technical nuisance, it's a philosophical wound. A reminder that the laws we treat as sacred may only be local customs, valid in our neighbourhood, but not beyond the horizon. In the next part, we'll dive into the escape attempts, how physicists have tried to replace the singularity with something gentler. Loop bounces, fuzzballs, and even wild speculations about black holes spitting matter back into new universes. Because if infinities are warning signs, then following them might lead us not to an end, but to a door. Let's open that door, the one marked singularity, and see what physicists have tried to build behind it. Because while Einstein's math points to an infinity, not everyone is satisfied leaving it there like a blacked-out page in the universe's diary. One candidate is loop quantum gravity, LQG, the idea that space-time itself is not smooth but granular, like Lego bricks too tiny to see. According to LQG, you can't squeeze space infinitely. There's a fundamental unit, a smallest pixel of geometry. Push beyond that, and the equations push back. Instead of a singularity, you get a bounce. Matter collapsing inward might rebound, turning the death core into a quantum trampoline. Some versions even imagine that this bounce doesn't just vanish, but erupts as a new expanding universe on the other side. In that picture, every black hole could be a womb. Then there's string theory's fuzzball hypothesis. If particles are not points but strings, then a black hole is not an empty cavity with a singular spike at the centre. It's a tangled ball of vibrating filaments, a fuzzball. No smooth horizon, no singular core, just a dense quantum hairball. According to this idea, every detail of the matter that fell in is smeared across the fuzz, like tattoos on a cosmic skin. Information isn't lost, it's embedded. The black hole, in this version, is less like a bottomless pit and more like a very dense, very exotic star with a fuzzy boundary. Sound strange? That's because it is. But strange is what happens when your two best theories, quantum mechanics and general relativity, refuse to cooperate. One says no infinities allowed, the other says singularity is inevitable. Reconciling them requires inventing possibilities that feel closer to myth than mechanics. There are also whispers of more radical visions. Some researchers speculate that matter falling into a black hole doesn't vanish at all. It tunnels through space-time and emerges elsewhere, perhaps in a white hole, the time-reversed cousin that spews matter instead of swallowing it. Others dream bigger. Every singularity could be the seed of a new universe, a cosmic Russian doll. In this scenario, our own Big Bang might have been the rebound of a collapsing star in some larger cosmos. Do we have evidence? Not yet. These are not telescopes but thought experiments. The bounce of LQG or the fuzz of strings hasn't been observed in any black hole we can point a radio dish at. But even without data, these models matter, because they remind us that singularity is not the end of the conversation, only the placeholder until we find better language. And here's the curious thing. Though these ideas diverge wildly, they share a common theme. Singularities are lies. They're not real features of the universe, just the signposts telling us our current tools are breaking. Like a calculator flashing error when asked to divide by 0. The true picture is waiting in the theory we haven't finished writing. Which leaves us with a tantalizing cliffhanger. If the core of a black hole is not a
宇宙に
singularity,
はおよそ
then
2
what is it
兆の銀河
really?
が存在する
Is
こ
it a
とについ
bounce
て
into another world?
皆さんは考えたことはあり
Fuzzball
ますか？
smeared with information?
私たちの
Or a
天の
white
川
hole
銀河
like
は
geyser
その中
spraying
の一
matter
つに
into
過
the
ぎま
far
せん。
future?
そう、
In
こ
the
の
next
銀河は
chapter, we'll
私た
step
ちの宇
beyond
宙の
theory
家。
into
し
speculation's
かし、
twilight.
純粋に理論
What
上
if
は
black
同
holes
じ
are
確
not
率で
ends,
別の銀河に
but
住んでいた
beginnings?
可能性もあるのです。
Could every black hole
皆
be
さん
the
こんに
seed
ち
of
は。
another universe?
仮にそうだっ
And
た
are
と
we
したら、
perhaps the
地球は
descendants
ど
of
んな影響を
one
受けたので
such
しょうか。
collapse? Now
な
let's
ぜ
wander into
活動銀河核
speculation's
を持つ銀
twilight,
河は知
where
的生命
physics
体を
slips
探
into
すのに
myth
適
but
さないので
refuses
しょ
to
うか。
admit it.
皆さん、
If
こちらはトップ
singularities
ラン
are
キングです。
illusions,
今回はその
what
すべて
really
と
lies at the heart
他
of
に
the
も
black
たくさんの
hole?
話題をお届けします。
One provocative
それでは
possibility
始め
is
ま
the
しょう。
cosmic bounce. Loop quantum gravity paints this picture. As matter collapses inward, space-time itself resists infinite compression. Instead of hitting a dead end, the collapse rebounds, creating a new expanding region of space-time. In other words, a baby universe, budding from the womb of a dying star. Black holes as cosmic seeds. To us on the outside, it looks like annihilation. To whatever emerges beyond, it looks like Genesis. Then comes the white hole scenario. Imagine a mirror twin of the black hole, not a consumer, but a spitter. Instead of swallowing everything, it ejects matter with contempt, a geyser of creation. White holes are the time reverse of black holes, solutions that Einstein's equations technically allow, though we've never seen one. Some theorists dream that the singularity inside a black hole tunnels into a white hole in another patch of space-time. What falls in here gushes out there, like a cosmic plumbing system with no respect for our sense of place. And let's not forget string theory's fuzzball approach. No sharp horizon, no core, just a ball of quantum threads, dense and knotted. In this vision, the black hole is not a doorway, but an exotic star, with every detail of what fell in etched into its tangled surface. From the outside, it still looks like a black hole, but the inside story is radically different. No singularity, no oblivion, just fuzz. Each idea offers a way to banish infinity, but each raises new puzzles, If black holes spawn new universes, can those universes ever talk back? If white holes exist, why haven't we seen their tantrums spraying matter into our sky? If fuzzballs are real, how could we distinguish them from the classic black hole we think we've already photographed? What's striking is how mythic these theories feel. A cosmic womb, a mirrored geyser, a fuzzy star. They read like allegories, and yet they come straight from our best attempts to stitch quantum mechanics and gravity together. When physics pushes against its boundaries, it often ends up speaking in poetry. But let's ground ourselves. No telescope has yet confirmed a bounce, a fuzzball, or a white hole. What we do have are clues: gravitational waves from colliding black holes, shadows caught by the Event Horizon telescope, and these clues so far look very much like the standard black holes Einstein described. Still, the door isn't closed. Perhaps the differences are too subtle for current instruments. Perhaps the universe hides its strangeness better than we imagined. And here's the haunting part. If black holes really birth new universes, then ours might be the child of another cosmos's collapse. We might be living in a second-generation universe, a rebound from a parent black hole. That would make the Big Bang not the absolute beginning, but the passing of a torch. Speculation? Absolutely. But speculation with teeth. Because each of these visions, bounce, fuzzball, white hole, doesn't just explain away the singularity. It hints at a richer, stranger reality than Einstein ever dreamed. In the next section, we'll step out of theoryland and back to observation. How exactly did humanity see the unseeable? How did we photograph the shadow of a black hole if by definition no light escapes? That story, 2019, M87er, and a donut of fire, is its own paradox worth savouring. All right, let's step back from the speculative wombs and fuzzy balls and walk into something more concrete, or at least more photographic. Because in 2019, humanity did something absurd. We saw a black hole. Now pause on that sentence. By definition, black holes are invisible. They trap light. They're the ultimate camera-shy celebrities of the cosmos. And yet, the Event Horizon telescope collaboration, an orchestra of radio telescopes spread across the planet, managed to stitch together an image of M87Q, a supermassive black hole, 55 million light-years away. The picture went viral. A fiery orange ring, glowing plasma circling an empty dark core. To the untrained eye, it looked like a slightly blurry cosmic bagel. To physicists, it was history. A confirmation that Einstein's equations, once again, refused to quit. But here's the paradox. If no light can escape, what exactly were we looking at? The answer lies in the neighbourhood around the black hole. Matter spiralling in doesn't fall silently. It heats up to billions of degrees, emitting light across the spectrum. That's the accretion disk, a maelstrom of gas swirling at relativistic speeds. The black hole's immense gravity bends and warps this light, wrapping it into a luminous halo. The central darkness is not the black hole itself, but its shadow, the region where light paths are swallowed rather than bent toward us. And that ring, it's not arbitrary. Its size, its circularity, even its brightness profile match predictions from general relativity. Einstein, long dead, got another win. The ring was about 2.5 times the radius of the event horizon, exactly as theory predicted. That blurry bagel was an empirical triumph. Of course, scientists weren't content to just pat themselves on the back. Some skeptics asked, could it be an illusion? Could the algorithms have stitched the data into a donut simply because we expected one? The EHT team anticipated this critique. They ran multiple independent reconstructions, cross-checked with theory, and kept observing. And when they looked at our own Milky Way's black hole, Sagittarius A, they found another donut. Coincidence? Hardly. Still, let's not forget the humour in all this. After the first image was released, the internet dubbed it everything from a cosmic eye to the Eye of Sauron. Some said it looked like a Halloween decoration. My personal favourite, the universe's first attempt at latte art. Science may be serious, but memes remind us it's still very human. But beyond the jokes, the achievement was staggering. Telescopes on different continents had to synchronize to a fraction of a second using atomic clocks. Data so massive it couldn't be sent over the internet had to be shipped by plane on hard drives. And after years of work, the result was a picture that told us, yes, black holes exist. And they look exactly as predicted. And yet, because black holes are black holes, the paradox lingers. We didn't actually see the black hole. We saw its influence, its gravitational lensing of the plasma, its shadow carved out of surrounding light. It's like seeing a monster only by the footprints it leaves. Compelling, yes, but still indirect. Which raises the next question. Is that enough? Can we be certain that these donuts are true black holes and not impostors, graver stars, boson stars, or some other exotic mimic? That's the next battlefield. Because if physics has taught us anything, it's that the universe loves to leave just enough doubt to keep us arguing. In the next part, we'll sit with those doubts. We'll explore the skeptic's corner. How reliable is the donut? And could we have mistaken an exotic imposter for Einstein's black hole? The fiery donut of M87 volts was a triumph, yes. But in science, triumph always comes with a disclaimer. What if we're wrong? The skeptics weren't silent after the Event Horizon Telescope's big reveal. Some muttered, "You didn't actually photograph the black hole. You photographed plasma, bent by gravity and reconstructed by algorithms. What if the donut is a mirage?" It's a fair question. The EHT didn't snap a Polaroid. It assembled radio waves gathered across Earth into a single picture using interferometry. That process is delicate. Imagine recording a symphony using microphones scattered across the globe and then trying to reconstruct the music perfectly. Possible, yes, but open to suspicion. So could the ring be a false echo, an artifact of assumptions baked into the algorithms? The EHT team anticipated this. They ran their data through multiple independent pipelines, blind to each other's expectations. They used different image reconstruction methods, different theoretical priors, and every time a ring appeared. Not identical, but consistent enough that the skepticism began to soften. But even if the picture is real, another question lurks. What caused the ring? The official answer, a black hole's shadow. But the universe doesn't only stock black holes. There are exotic alternatives that mimic them almost perfectly. Take graver stars, proposed in 2001. These hypothetical objects replace the singularity with a core of dark energy and a thin shell of matter. From the outside, they look nearly indistinguishable from black holes. Their gravitational pull, their lensing of light, their shadowy outlines, almost the same. Or boson stars, clusters of ultralight particles bound by gravity and quantum pressure. They too can bend light into rings, and they lack horizons. Drop matter onto one, and instead of vanishing forever, it would splatter on a surface, though from 55 million light-years away that difference may be hard to detect. So when we saw that donut, were we really seeing a black hole? Or one of its impostors? The honest answer, we can't be 100% sure. The EHT's resolution is good, but not infinite, and so far, all the data we have, rings, shadows, gravitational waves, fit black holes beautifully. They also could fit some impostors if you squint. But here's where the skeptics run out of road. Black holes don't just produce pretty pictures, they sing. When they collide, they send ripples in space-time, gravitational waves that ring like cosmic bells, and those ring-downs, detected by LIGO and Virgo, have matched the notes predicted by Einstein's black holes with eerie precision. Graver stars or boson stars would leave slightly different signatures, subtle echoes, extra vibrations. So far, those haven't appeared. Still, science is cautious. We say, evidence overwhelmingly supports black holes, but we keep the door cracked. Because keeping doubt alive is not weakness, it's the strength of science. It's what prevents us from turning today's triumph into tomorrow's embarrassment. So let's hold the paradox in both hands. We have seen shadows that shouldn't be visible, we've heard space-time ring like a drum, and everything lines up with Einstein's black holes. Yet we admit, Perhaps, hidden in the noise, an imposter waits. In the next section, we'll trade images for clocks, because if pictures raised eyebrows, time itself around black holes raises entire paradoxes. How can two observers witness the same fall, one seeing it freeze forever, the other plunging straight through? Welcome to the temporal funhouse. Time, the one thing you thought you could count on, the ticking metronome of existence. Around a black hole, time laughs in your face. Here's the setup. Imagine an astronaut, let's call her Elena, falling toward a black hole while her friend Amir watches from a safe distance. Amir sees Elena approach the event horizon and slow down. Slower, slower, until, at the very brink, she seems to freeze. The last photons of her image crawl to a red smear, stretching into invisibility. From Amir's perspective, she never crosses. She just hangs there,
宇宙に
an
は
eternal
およそ
sculpture
2
at
兆
the
の
edge.
銀河が存在することについ
But
て
Elena,
皆さん
her
は考
clock
え
ticks
たことはあります
normally. She
か
feels the fall.
私たち
She
の
doesn't
天の川
freeze at
銀
the
河は
horizon.
その中の
She
一つに
plunges
過ぎません
through. No drama
そう
at the crossing.
この銀河は
No sudden
私たちの
burn.
宇宙の家
Just a steady
しかし
acceleration into deeper
純粋に理
darkness.
論上は
For
同
her,
じ確
the
率
end
で
comes
別
not
の
at the
銀河に住んでい
horizon,
た
but
可
at
能
the
性もあるのです
singularity.
皆
Or
さんこ
whatever
んにちは
lies in its place.
仮にそうだった
Two
としたら
perspectives,
地
both
球はどんな影
valid,
響を受けた
both
のでしょうか
contradictory.
なぜ
Which one is
活動銀河核を持つ銀河は
Physics
知的
shrugs
生
and
命体を
says
探すのに適さないのでしょ
General
うか
relativity allows
皆
it.
さんこちらはト
That's
ップ
the
ランキン
time
グです
dilation paradox.
今回はそのすべて
What
と
seems eternal
他に
from
もたくさん
outside
の
is
話題をお
fleeting
届け
from
します
within.
それ
It's
では始め
unsettling
ましょう
because it bends our intuition about cause and effect. For Amir, the universe keeps Elena suspended forever, her story unfinished. For Elena, the story ends quickly. One reality, two timelines. It's like watching a movie where the main character dies in 10 minutes, but from your seat, the film never actually reaches that scene. Now add another wrinkle, gravitational redshift. The light Elena emits as she falls grows fainter, stretched to longer wavelengths, until Amir can no longer see her. It's as if the universe itself senses the ending, refusing to show the final frames. And then there's causality. Inside the horizon, all paths point inward. You can't send a signal back to the outside. You can't even scream into the void and hope it echoes. From Elena's perspective, she can still live her last moments. From Amir's, her story is sealed off, never influencing the outside world again. Cause and effect are amputated at the horizon. This is why physicists sometimes call black holes time machines of a cruel sort. They don't let you travel to the past or future in a playful sci-fi way. Instead, they distort time itself so that different observers live in irreconcilable narratives. And this isn't just philosophy. The mathematics predicts it. Time dilation near massive objects has been tested. Atomic clocks on airplanes tick differently than those on the ground. GPS satellites correct for it daily. A black hole is simply the ultimate case, a place where the difference becomes infinite. Speculative minds have taken this further. If black holes mess with time, could they also connect times? Cue the wormhole hypothesis. Perhaps the interior of a black hole links to another region of spacetime, a shortcut, a bridge, maybe even a way to the future, or another universe. That's the science fiction version. The sober version says, the tunnel collapses too fast to be useful. Unless you have exotic matter to hold it open, and exotic matter is, well, still exotic. Yet the allure lingers. Black holes don't just bend space, they twist the narrative of time itself. They remind us that what feels absolute, cause before effect, present before future, is just another local custom. At the edge of a horizon, the universe rewrites its grammar, and if that wasn't unnerving enough, there's another paradox waiting. What if the black hole itself doesn't exist the way we think? What if, after all these decades, the very object we've built theories around is just a convincing impostor? That's the existential crisis waiting for us in the next part. So here we are, staring not at the singularity, not at the fuzz, not even at the fiery donut, but at time itself, the quiet saboteur in this whole story. Because black holes don't just eat matter, they mess with the order of events, the very grammar of cause and effect. Let's return to our astronaut Elena and her friend Amir. From far away, Amir's telescope shows Elena suspended at the edge, frozen forever at the horizon, her image fading redder and redder until the universe itself pulls the plug. For him, she never crosses. For her, though, the horizon is no wall. She falls through in a finite number of heartbeats. Inside, time ticks, reality continues, at least until the singularity, or its replacement, ends her journey. Two narratives, irreconcilable, yet both allowed. This isn't a glitch in the simulation, it's relativity working as advertised. And it gets weirder. From Elena's point of view, as she crosses the horizon, the outside universe appears to speed up. She would, in principle, watch distant galaxies age, stars live and die, civilizations rise and fall in what seems like fast forward. She dives in, and the cosmos races ahead. To her, the black hole is less a prison than a time machine that only moves forward. But the story cuts sharply. She cannot send word back. The horizon amputates communication. From inside, her cries are sealed. From outside, her fate is sealed. The chain of cause and effect breaks. Black holes don't just warp time, they fracture it. Physicists call this the causal disconnection. Events inside cannot influence events outside. Whatever dramas unfold beyond the horizon, collapsing stars, quantum fireworks, whispered bounces, remain trapped. The outside universe goes on without them, as if that piece of space-time had been snipped from the causal web. And this leads to another temptation. If horizons slice reality into disjointed theatres, could they also stitch other theatres together? Enter the wormhole hypothesis. The mathematics of general relativity permits Einstein-Rosen bridges, tunnels connecting distant points, or even entirely different universes. In principle, a black hole could be the mouth of such a bridge, its twin a white hole spewing matter elsewhere. To science fiction, this is irresistible. To physics, it's tantalizing but fragile. Wormholes, if they exist, collapse too quickly for anything to pass through, unless, of course, we find exotic matter to prop them open. And exotic matter is so far as mythical as unicorns. Still, the metaphor holds. Black holes are places where time stops making sense in the ordinary way. To one observer, eternity. To another, a fleeting fall. To some, frozen images. To others, fire and collapse. What is real? Both, and neither. Reality becomes relative in the most literal sense. And this is why black holes gnaw at philosophers as much as physicists. They force us to ask, is there such a thing as the story of the universe, or only versions told from different vantage points? Does truth itself bend under gravity? In the next section, we'll embrace that existential doubt and step into the boldest paradox yet. What if black holes, the very objects we've been obsessing over, don't exist at all in the way we think? Could all of this be a mirage? Nature teasing us with lookalikes? After all these paradoxes, information loss, singularities, time gone strange, you'd think the one thing we could cling to is this. Black holes exist. They're real. We've seen their shadows, felt their gravitational waves, mapped stars whipping around invisible anchors. Surely they're out there. And yet, here comes the final paradox, the cheekiest of them all. What if black holes, as Einstein described them, don't exist at all? This isn't a crank theory. It's a minority position held by serious physicists. The argument goes like this. Black holes, as defined, require two brutal ingredients, an event horizon and a singularity. But both bring trouble. Horizons hide information. Singularities break physics. Maybe nature, cleverer than us, avoids these headaches by never allowing a true black hole to form in the first place. So what would we see instead? Enter the impostors. The first candidate, graver stars. Imagine collapse arrested just before the horizon forms. Instead of a singularity, the star stabilizes with a strange core of dark energy, wrapped in a thin shell of matter. To distant eyes, a graver star looks almost identical to a black hole. It bends light, it casts a shadow, it herds stars in tight orbits. But inside there's no singularity, no horizon, just a weird, stable bubble. Next up, boson stars. These hypothetical objects are made of ultralight particles, bosons, that don't behave like ordinary matter. They can overlap and form a dense, coherent blob. To telescopes, they could mimic black holes, lensing light and swallowing matter. The difference? Boson stars have a surface. Drop something onto one, and it smacks into the surface and radiates energy rather than disappearing forever. There's even talk of dark stars, not in the 18th century John Michel sense, but as theoretical beasts powered by dark matter in the early universe. They'd be massive, compact, and dim, easy to confuse with black holes if you're squinting from billions of light years away. These impostors aren't just wild guesses. They're motivated by the very paradoxes we've walked through. If information loss and singularities are unacceptable, maybe nature found a loophole. Maybe what we call black holes are just convincing fakes, objects that imitate all the external features while skipping the problematic internals. But the evidence? That's the problem for the skeptics. The orbits of stars near Sagittarius A in our galaxy, the ring-shaped shadow of M87, the gravitational waves from LIGO, all of them match Einstein's black holes perfectly. The ringdowns we've heard, the dying tones of merging giants, sound exactly like black holes, not impostors. If alternatives exist, they have to mimic the real thing with uncanny precision. Still, science thrives on such doubt. Even Stephen Hawking, late in life, mused that perhaps strict event horizons don't exist, that maybe the edges are fuzzy, fluctuating, letting information leak more gently than we imagined. It wasn't denial, it was humility before the complexity of quantum gravity. So the paradox isn't just do black holes exist, it's subtler. Do they exist in the way we've always pictured them? The truth might be messier, horizons may not be perfect, singularities may be mirages, the universe may have patched over infinities with quantum stitching. And that's why black holes remain the strangest mirrors we've ever looked into. They don't just reflect light, they reflect the cracks in our theories, showing us where knowledge ends and imagination begins. In the next part, we'll turn from doubt to evidence, because while imposters are intriguing, the data keeps piling up in favour of the real deal. And every new gravitational wave, every sharper shadow, draws the noose tighter around the neck of alternative theories. Let's turn from the courtroom of doubts back to the evidence, the pile of receipts the universe has been handing us for decades. Because if graver stars, boson stars, and other imposters want to steal the stage, they need to act better than the originals. And so far, Einstein's black holes are winning all the auditions. Take the gravitational waves. In 2015, LIGO made history by detecting the faint ripples from two black holes colliding over 1 billion light-years away. That signal, the famous chirp, wasn't just a cosmic melody, it was a test. After the merger, the newborn black hole rang like a bell, a phenomenon called the ringdown. The frequency and damping of that ringdown matched Einstein's predictions for a Kerr black hole almost perfectly. If the object had been a graver star or boson star, the ringdown would have been slightly off-key, leaving faint echoes or distortions. None were found. Then there are the stars orbiting Sagittarius A, the monster at the centre of our Milky Way. Astronomers have tracked them for decades, watching them whip around an invisible point with dizzying speeds. One star, S2, has been especially faithful, tracing an elliptical orbit every 16 years. Its path, its precession, even the way its light
宇宙
redshifts
に
near
は
closest
およそ2
approach.
兆の銀河が存在
All of
する
it
ことに
lines
つい
up
て
with Einstein's
皆
black
さんは
hole
考
model.
えたことはありますか？
An imposter would have
私
to
たちの
mimic
天
this
の川
dance
銀
step
河
for
は
step,
その中の
note
一
for
つに
note.
過ぎません。
And of course,
そう、
there are the
この銀
shadows.
河は私たちの宇宙
M87
の
in
家。
2019,
しか
and
し、
Sagittarius
純粋に理論上は
in
同じ確
2022.
率で別の銀
Two
河に住ん
different
でいた可能
galaxies,
性もある
two
のです。
different masses,
皆さんこん
same
にちは。
theory donut.
仮にそうだったとしたら、
That
地球
consistency
はどんな
isn't
影響を受けたので
coincidence.
しょうか？
It's the
なぜ
universe
活
saying,
動銀河核を持つ銀河は
Yes, this is the
知
real
的生命体を探すのに適さないので
science
しょう
isn't
か？
about piling up
皆さん、
confirmations and
こちらは
declaring
トップ
victory
ランキングで
forever.
す。
It's
今
about
回はその
probing
す
the
べてと
edges,
他にも
keeping
た
the
くさんの話
possibility
題を
of
お届けし
imposters
ます。
alive until they're
それ
ruled
で
out
は始めまし
decisively.
ょう。
Some researchers still scan gravitational wave data for faint echoes. Others model how plasma would behave near graver stars, checking whether future telescopes could spot the difference. The chase continues, not because physicists want black holes to be fake, but because testing the limits is how you learn what's real. And let's be honest, imposters would be fascinating. Imagine discovering that what we thought were black holes are actually something stranger, a window into new physics. It would rewrite textbooks, redefine cosmology, maybe even explain dark matter. But the bar is high. Every observation so far strengthens Einstein's version. The alternatives remain shadows of shadows, whispers against a roar of evidence. So the existential paradox remains unsolved in spirit, but leaning heavily toward one answer. Black holes exist, and they are as terrifying and magnificent as general relativity described. Still, the doubts, tiny though they are, keep the conversation alive, ensuring that the story of black holes is never finished. In the next part, we'll leave the courtroom behind and look ahead. Because the real question now isn't do black holes exist, but what will the next generation of observations reveal? With sharper eyes and better ears, humanity is about to eavesdrop on the universe in ways Einstein never dreamed. So, if black holes are the frontrunners, what's next? What new tricks can we pull to make sure we're not just fooling ourselves with cosmic donuts and chirps in the void? The future of black hole science lies in sharper eyes and better ears. Let's start with the eyes. The Event Horizon Telescope, EHT, isn't done. The 2019 donut was just a teaser trailer. Plans are already underway for a next-generation EHT, adding more telescopes across the globe and even some in orbit. Imagine swapping your blurry VHS tape for an 8K livestream. Soon, we won't just see static images of black holes. We'll see movies showing plasma whirling around horizons in real time. Picture watching the universe's deadliest drain swirl in motion. And then there are the ears, gravitational wave detectors. LIGO and Virgo opened that door, but upgrades and new observatories are coming. In the 2030s, the Laser Interferometer Space Antenna, LISA, will float in space, measuring ripples with the precision of a cosmic violin tuner. Unlike ground detectors, LISA will catch waves from the heaviest black holes in the universe, supermassive giants merging in galactic collisions. These signals will last for months, not seconds, giving us symphonies instead of chirps. Together, these tools will do more than confirm black holes. They'll test them to the breaking point. Do they really ring like Einstein said? Do their shadows always match relativity's script? If they don't, then the cracks appear, and maybe graver stars or boson stars get a second audition. But let's not forget the most mischievous frontier, quantum information. Physicists are now asking whether black holes might be cosmic data vaults. Could the Hawking radiation, the faint glow leaking from their horizons, carry hidden imprints of what fell in? Could information escape, not in a flood, but in whispers? This is where ideas like the island formula come in, suggesting that information is encoded in subtle correlations in radiation. If true, it would resolve the decades-old paradox and prove that black holes are less like cosmic shredders and more like cosmic archivists. All of this, sharper images, richer waveforms, quantum whispers, points to one conclusion. The 21st century might be the golden age of black hole science. We've moved from guessing to photographing, from metaphors to measurements, and with every step the universe rewards us with confirmation and contradiction in equal measure. In the next part, we'll step back and ask the bigger question. What do black holes tell us not just about physics, but about ourselves? Why are we so drawn to these cosmic monsters, and what do they reveal about the way humans confront the unknown? Step back for a moment. Why are we so obsessed with black holes? Why do they haunt our movies, our memes, our late-night YouTube binges? On paper, they're just astrophysical objects, collapsed stars, solutions to Einstein's equations. But culturally? There's so much more. Black holes are the universe's way of trolling us. They're the cosmic do not enter sign. The one place where our laws of physics fold up and mutter, "Good luck." That alone makes them irresistible. Humans are wired to poke the forbidden. If the cosmos says, "Here's a place you'll never see inside," we immediately build billion-dollar telescopes to peek anyway. They also hit something primal in us, fear of the void. Ancient myths always featured bottomless pits, dark abysses, monsters that swallowed entire worlds. Black holes are the modern, scientific version of that archetype. They are literal abyss incarnations, so dense, so dark, so final, that they feel like myth made real. And then there's the allure of extremes. Black holes aren't just objects, they're limit cases. The fastest time dilation, the strongest gravity, the hottest disks, the most energetic jets. They sit at the boundaries of what's possible, and humans love boundaries because they promise secrets. Whenever we find an edge of the map, we can't resist leaning over. But black holes also reflect something about us, our discomfort with not knowing. For centuries we believed the Earth was the centre, then the Sun, then the galaxy. Each time, science humbled us. Black holes are another humbling. They remind us that there are places where we can't go, where our tools falter, where reality itself grows fuzzy. They whisper, "You don't know everything, and maybe you never will." And that paradox, the mix of fascination and fear, is why black holes loom so large in our imagination. They are scientific objects, yes, but they've also become cultural symbols. They show up in sci-fi as gateways, in philosophy as metaphors for death or the unconscious, in comedy as that place where your socks vanish. Everyone has a version of the black hole. So maybe the real story isn't just about event horizons and quantum paradoxes. Maybe it's about why we, as humans, keep staring into the abyss, knowing it won't stare back. Because every time we try, we end up learning more about the universe, and strangely enough, about ourselves. In the next part, we'll bring everything together, the paradoxes, the evidence, the doubts, and the wonder. And we'll ask the final, unanswerable question, are black holes the ultimate truth of the universe, or just another stepping stone on the way to something stranger still? So here we are, at the end of our long descent into the abyss. We've followed the breadcrumbs, paradox after paradox, theory after theory, until black holes feel less like astrophysical objects and more like a mirror held up to our ignorance. Think of the paradoxes we've walked through. Information that should never disappear but seems to vanish. Singularities that crush equations into nonsense. Time that runs both forever and instantly, depending on where you stand. Shadows we can see but not touch. And finally, the possibility that the very things we call black holes are impostors wearing perfect masks. Every one of these contradictions screams the same message. Our theories are incomplete. General relativity, magnificent as it is, buckles at the singularity. Quantum mechanics, powerful as it is, sputters at the event horizon. Black holes are the pressure cooker where our two greatest frameworks go to war. And yet, this is why scientists love them. Because paradoxes aren't dead ends, they're invitations. The information paradox spurred the holographic principle, reshaping how we think about spacetime itself. The singularity problem pushes us toward quantum gravity, string theory, loop theory, dreams of unifying the big and the small. Even the skeptics, impostors, graver stars and boson stars force us to sharpen our definitions and test our models. Black holes, in other words, are not just monsters in the dark. They are teachers. Stern teachers, sure, the kind who toss your homework in the fire and dare you to reconstruct it from the ashes, but teachers nonetheless. And maybe that's why they fascinate us. They embody both ultimate destruction and ultimate possibility. They swallow matter, light, even time itself. But they also give us tools, gravitational waves, fiery rings, that let us peek into physics we've never touched before. They are both tombstones and birthplaces, where stars end and where new theories begin. So, are black holes the ultimate truth of the universe, or just stepping stones towards something even stranger? Structures we haven't yet imagined, laws we haven't yet written? The honest answer, we don't know, Not yet. But perhaps that's the point. Science isn't about having the final word. It's about the chase, the thrill of chasing donuts in distant galaxies, the joy of listening to spacetime hum, the stubborn refusal to let mysteries sit unsolved. Black holes give us the perfect chase, impossible to touch, irresistible to pursue. So the next time you see that fiery ring, remember, it's not just a photograph of a black hole. It's a photograph of human curiosity itself, burning bright around the darkest place in the universe, and that maybe is the real paradox. Black holes may be the end of everything, but they're also the beginning of our most daring questions. So what do we do with all of this? The donuts, the paradoxes, the whispers of information, the gravitational symphonies. Do we tie it neatly with a bow and declare, solved? Hardly. Black holes don't give neat endings. They are by definition cliffhangers. Because here's the truth. Every paradox we've explored still hangs in the air. Information loss? Maybe fixed by holography, maybe not. Singularities. Still hiding in the math, waiting for a quantum gravity theory to unmask them. Time dilation. Confirmed in principle, impossible to reconcile with intuition. Shadows. Captured, yes, but still open to interpretation. Existence itself, backed by overwhelming evidence, but always with that sliver of doubt. And maybe that's the most honest way to end. Not with answers, but with questions sharpened to a point. In the 21st century, we finally turned black holes from metaphors into data. We didn't just theorize, we imaged, we recorded waves, we measured orbits. And what did all that get us? More paradoxes. But paradoxes are good. They're signposts that say, here, dig deeper, something's missing. Perhaps one day a unified theory, quantum gravity, string landscapes, loop lattices, will stitch the contradictions together. Perhaps future telescopes and gravitational wave detectors will expose impostors or confirm Einstein once and for all. Perhaps, just perhaps, black holes will turn out to be something entirely different, stranger than both physics and fiction have dared to dream. Until then, black holes remain the universe's greatest magic trick. They swallow light, time, and matter, and in return they give us wonder. They lure us into midnight debates, into equations scribbled on chalkboards, into billion-dollar telescopes aimed at distant voids. They are both the ultimate endings and the ultimate beginnings. So the next time you look up at the night sky, remember, somewhere, out there, stars are collapsing, horizons are forming, and paradoxes are being born. And humanity, stubborn as ever, will keep chasing those paradoxes into the dark, whispering, "We're not done yet.